There's two examples. The first example is multivariate scalar valued function. Herein we can see that f of x is defined to be equal to x transpose x, which is the self dot product, and this vector is a three-dimensional vector. So we would like to find out its gradient. Well, since it is a scalar valued function, so we are going to find its gradient, which would mean that I am going to write, first of all, I'm going to calculate all the partial derivatives of this function with respect to each independent variable. So the dependency on this vector is, and this vector is three-dimensional, therefore I'm going to calculate these partial derivatives, which are three in number. So partial derivative of f with respect to x1, partial derivative of f with respect to x2, and partial derivative of f with respect to x3. So I need to calculate these entities and put them into this matrix, and I'm going to get the gradient of this function under discussion. Since we know that this self dot product is the sum of the squares of the individual components, therefore when I will be calculating the partial derivatives, I'm going to get some expression of this type which says that df by dxj is going to be equal to 2xj. Primarily, if you look into this statement, it is clear from here that if I am calculating the partial derivative with respect to x1, the two terms containing x2 and x3 are not going to contribute because their partial derivatives with respect to x1 are going to be equal to 0, and that would mean that the partial derivative of this x transpose x with respect to x1 is going to be equal to 2x1. Similarly, the partial derivative of x transpose x with respect to x2 is going to be 2x2, and partial derivative of x transpose x with respect to x3 is going to be 2x3. So, which in general is written in this format, that partial derivative of f with respect to xj is equal to 2xj. Since I have calculated all of these values and I put them into one row matrix, I get this thing, that the gradient of f with respect to x is 2x1, the first component, 2x2, the second component, 2x3, the third component. We can take 2 common outside, and then I'm left with the row matrix x1, x2, x3, which is primarily the transpose of this vector x. So if I have any dimensional vector, it could be 3, 4, 5, 6, any dimensional vector, and I'm calculating the gradient of the self dot product, it is going to be equal to 2x transpose irrespective of their dimensions. So this was one example of the gradient of multivariate scalar valued function. So that was example number one. And example number two is from the book, and it is example 5.9 on page 153. Here we are going to calculate the gradient of multivariate vector valued function. So that would mean that the input of the function is also consisting of more than two components, two or more components, and the output of the function would also be consisting of two or more components. So here in this case, we have that this function is defined to be equal to f of x equals ax. So that would mean that I am actually looking at the matrix vector multiplication. And it is given that this matrix A happens to be a 2 by 3 matrix. So it would mean the input to this matrix, the input to this function is a three-dimensional vector, and the output of this function is a two-dimensional vector. So primarily this function f is from three-dimensional Euclidean space to two-dimensional Euclidean space, which is explicitly written over here, is that okay, for any x consisting of x1, x2, x3, which is a three-dimensional vector, the output is going to be equal to x1 plus 3x2 plus 4x3, the first component of the function, 2x1 plus 3x2 plus 6x3, the second component of the function. So if I write them explicitly, what would I get? I would say that the first component of this vector valued function is x1 plus 3x2 plus 4x3, and the second component of this vector valued function is 2x1 plus 3x2 plus 6x3. Well, now gradient of the multivariate vector valued function is primarily a Jacobian, and we have already seen in our previous lectures that the Jacobian of such a function is a matrix, and in this case it's a 2 by 3 matrix. So the first row is reserved for the gradients or the partial derivatives of the first component of the function. and the second row of this Jacobian is reserved for the gradients of the second component f2 of the function. So you would see that if I look at the first row of this Jacobian, it is simply the collection of the partial derivatives of the first component, and the second row is reserved for the derivatives of the partial derivatives of the second component. And otherwise, if you look at the first column, you would see that it is primarily the vector derivative of the function with respect to x1, and the second column of this matrix or this Jacobian is the vector derivative of the function with respect to x2, and the third column is the vector derivative of the function with respect to x3. So now I know the individual values for f1 and f2, and I need to calculate these partial derivatives, which in general would become that, okay, partial fi by partial xj. So that would mean that I need to calculate all of these six partial derivatives. By the way, if you just look into this first line over here, which is f1 to be equal to x1 plus 3, x2 plus 4, x3. So the partial derivative of f1 with respect to x3 is going to be 4. The partial derivative of f1 with respect to x2 is going to be 3. The partial derivative of f2 with respect to x2 is going to be 3. Well, once you have calculated all of these values, plug it into this Jacobian, what you're going to get, you're going to get 1, 3, 1, 3, 4, 2, 3, 6. Isn't it the same matrix that we already have, which is 1, 3, 4, 2, 3, 6? And therefore, we are going to say that the gradient or the Jacobian of this uh, multivariate vector valued function, which is ax, is equal to a. So that was the answer to that particular example. And the interesting thing is that at this point, this calculation that d by dx of ax to be equal to a also corresponds or corroborates with our normal day experiences when we are not multiplying a matrix to vector, but a scalar to some quantity. For example, if this was a scalar 5 and this was some scalar, just some scalar variable x, so I would have the d by dx of 5x to be equal to 5. So there is a correspondence over here. So these are the two interesting results that I wanted to discuss. So I hope that you have you would have understood it. Nevertheless, if there are any questions, please leave them in the conversation, in this thread of the conversation. Well, thank you very much.